where you are. So it's a pleasure for us to have today Erik Lindahl and Leonardo de Maria who will host this talk. First of all, I want to give some information previous we start. So since we have a lot of Latin people, Spanish speaking people, so we will give some notes in Spanish. So buenos días a todos y gracias por atender a nuestro seminario del día de hoy. Por favor recuerden usar sus nombres y apellidos de acuerdo a cómo se registraron en el formulario. Asegurarse de tener el micrófono en silencio. Ser respetuosos durante todo el evento. Si quieren realizar preguntas lo pueden hacer en el chat directamente. O alternativamente levantar la mano. Sin embargo, tenemos unas preguntas que las hicieron en el momento de registrarse y primero vamos a pasar estas preguntas antes de las preguntas que tengamos durante la charla. Si desean tener un certificado de asistencia, pueden solicitarlo enviando un correo desde la cuenta donde recibieron el link. Por favor, eviten compartir este link con otras personas o transmitir la charla a participantes que no estén registrados. Eviten capturar pantallas o redistribuir o transmitir datos sin el consentimiento del presentador. So, for the English-speaking people, so please use your first and last name according to how you were registered in the form. Mute yourself when you are entering the talk. Be respectful of other people. We can receive questions at the end of the talk. You can write it in the chat. Nevertheless, we have a set of questions that some of you submitted during the registration time. So we will first go through those questions. Please avoid to share this Zoom link with other people or broadcast the conference to unregistered participants. Avoid to capture, transmit, or redistribute data without the consent of the presenter. So thank you, everybody. And now I will let Leonardo start.
Thanks, Angelica. I'll also add that, once Erik starts talking, let's turn off the cameras and then just let only Erik's camera on. And then once the questions start, just please definitely feel free to turn on your camera so we can see you. Okay, so I think it's super good and great to have Erik here. I mean, it's a real pleasure, and I'll give a short introduction, but everyone essentially is aware of Erik and Erik's work. So he's professor of biophysics in the Department of Biochemistry and Biophysics at Stockholm University here in Sweden. His research focuses mainly in the study of membrane proteins in general, and in particular of ion channels and ion pumps. His group uses a number of techniques ranging all the way from bioinformatics to biomolecular simulations, and it works in very, very close connection with the experimental techniques, and all that in order to understand the molecular level interactions in these very complex membrane proteins. And at the same time, these experimental techniques include electrophysiology and spectroscopy to measure these functional effects and conformational transitions of the proteins, and with the goal again to see how mutations influence these proteins, or how can small molecules be designed to tune the properties of these compounds. This combination of techniques has been applied to a number of systems in Erik's team's work, and they have been able to determine how voltage-gated ion channels move between the intermediate states during opening, and also to show that there are separate binding sites for molecules that can either potentiate or inhibit the nerve signals in ligand-gated ion channels. And I think every one of you are very well aware that the team is also working with molecular simulation methodology development, and in particular, the very widely used GROMACS package, for which they are steering the international development team. And also Erik is very active in thinking about what are the next generation techniques that will enable us, for example, to use free energy calculations to predict binding and solvation energies. And I don't know if you know, but he has a YouTube channel where he posts some of his teaching. So you can also go there and pop up the number of followers. And without further delay, Erik, please, the floor is yours.
Thank you so much, Leo, Lucy, and everyone else. Great to see you. And well, it's great to be here, all of you. I have a ton of slides, so I'm going to get started right away. Let's see, share the screen first. Then we go with the presentation. Yeah, caveat emptor, I might or might not get through all these slides. It depends a bit on how much interruptions we have and if I drift away in other directions. But the point is to get a chat to talk with you and bring this in whatever direction we go. The slides are not necessarily important. It's always challenging. Oh, sorry. There, that looks better. And then I need to minimize that one. It's always challenging to give a presentation to a new community. And I realize that your background range from students to at least junior professors, maybe some senior ones too. So I will try to, there will be some low-level slides, intro slides and MD, but I'm going to try to formulate this a little bit in terms of some sort of modern molecular simulation, where I think we should go. Maybe some things that are not as obvious as they may seem when if you start reading chapter 1 of a manual or so. And well, some bottlenecks where things that haven't worked, things that I think have worked the last 2 years, and in particular where I think we should head in the future, both we in the sense of my careers and maybe some of your careers, because there's a lot of really exciting things remaining to do here. Let's see, yes. I will skip that coverage, but that's roughly what I'm going to talk about that I just told you. So as Leo told me, my background here is a bit special. So I started, as all of us, I started out as a PhD student. Once upon a long time ago, I was a theoretical physicist. I think I've lost my right to call me to use that label anymore. And then over the years, in parallel to getting larger toys in terms of small cluster and then large clusters and access to supercomputers, I've also been on some travels, first as a postdoc doing bioinformatics, then gradually starting to run a larger group. And somewhere over all these years, I started first dipping my toes, and I think now I'm roughly up to my waist in the experimental lab water. So full disclosure, I think almost half my lab is experimental nowadays. We're doing a lot of cryo-EM and electrophysiology. That is not because I think simulations are bad. On the contrary, I think we do better simulations now than we did 10 years ago. But interestingly enough, I think our simulations are frequently shorter, but I think we've learned to think a little bit more. So a common concept in simulation that might be more or less obvious, I keep going, is that we would like to model some sort of large life-scale processes or systems. In my case, things related to the nervous system and signaling there. Now, in general, there is no way we could model an entire nerve or cell, or even if there is, you so shouldn't do it. It's a very bad idea. And built into simulation is some sort of theoretical physical approach of reductionism, right? So take a complex system, reduce it to its parts, and if you can understand those parts, then we can at least in principle understand the entire system. I'm not entirely sure whether it's quite that trivial because biology is complicated. And one problem with that is simply, it's not entirely clear that we can simulate these things in the first place. It's very easy to load something in a program, whether it's GROMACS, Amber, and MD or so, it doesn't matter. And then run something and you're going to see something on the screen. It moves, you and or your professor will get happy. You might even get it published. But just because it's published doesn't mean that it's true. So I think at some point you either have thought about this or you should think about it if you're a student, so that in what way do you actually know that what you're seeing on the screen represents reality? And you can make an obvious comparison here to say hurricane forecasts. This is actually an area where the US was really worried some 10 years ago because the European codes were much better. The US had larger supercomputers though. And in particular, this Hurricane Sandy, most of the US projections actually missed that it would strike New York. And this is a bit fun because I was in New York at the time with my daughter. So we were actually there when the hurricane hit. But here you see, the whole width of all these individual predictions. You can't trust any of these predictions. But look at all of the predictions, we can kind of guess roughly where it's going to hit, right? And this is built into a whole of the physical systems. They're so-called chaotic, and virtually all many body systems are chaotic, and you can say that they have positive Lyapunov exponents. I mean, they will diverge exponentially if there's a tiny difference in starting conditions. And the problem is this is always going to be true for biological systems. You never know the starting conditions perfectly. And that means that you can't predict motion. And with that, we could in principle stop this talk, but I'm not going to do that. So the problem is that if you simulate this many times, you would end up with slightly different trajectories. And which one of this is true? Is it the blue or the red one? We don't quite know. So I think it is important to take a step back and pretty much forget about the concept that you can simulate motion. You're not trying to simulate motion. What you're really trying to do is take a complex molecule, well, not particularly complex, but not trivial molecule at least, and then somehow reproduce this in a phase space. So consider every possible conformation this molecule can be in, and what are the different energies. Now, if there was only one single conformation a molecule could be in, you would use quantum chemistry and you would get this super accurate. But for a large molecule, there are going to be a gazillion conformations that can be in, right? And it doesn't matter how accurate you know one of them, unless you know all of them. And that's really the whole reason why molecular dynamics simulations exist. We're pretty good at calculating all of them. So you could think of molecular dynamics simulation. This is really a poor man's way of doing Monte Carlo, testing many different conformations. It's pretty efficient at doing that. I won't have time to go into detail why, but in principle, we're just interested in mapping out every single possible conformation in phase space. Because if I understand all of phase space, then I understand the biological problems and I can predict which conformations are going to be good versus bad. In practice, we do this with some sort of simulation. There is whatever that you probably see. Those of you who have done MD have likely seen this, right? That you have some sort of fairly simple physical equations that describe the interactions between atoms. And then you need some sort of recipe, usually Newton's equation of motion, to just predict how this molecule is going to move. And this works fine, we think, at least if you believe that what we just saw there was representative of real motion. And this is really how you solve the problem in modern MD, that there is something called the shadow theorem, which is surprisingly undocumented, that the whole idea is that if the blue trajectory we have here, sorry for my extra yellow scribbling on the screen here, if the blue trajectory is the proper correct one, if we had an infinitely accurate starting point, that over reasonable timescales here, and whether this is 1 or 10 picoseconds doesn't really matter, but over some sort of reasonable timescales, if something starts out close to this blue path, it's not instantly going to go away from it. So that you're kind of tracking or shadowing the real trajectory reasonably close. We are not very far away from the true Hamiltonian, the entire description of the system. And you can actually prove this without hand waving. And because of this, simulations are not limited to just sampling all those conformations, but they can actually make predictions about the dynamics, kinetics, how fast things move. And that's why we can get diffusion and everything from simulations. So there is a ton of books you can read if you're really interested, but I think the short story is that we're not just hoping that you can predict the motion of one particle accurately. There is actually a sound theoretical basis why these individually uncertain simulations will do great at predicting both kinetics and structure. I will skip a little bit about this integration because there is a lot of interesting physics here, but I can just say that in hindsight, I think a lot of us went wrong here. So when I was a young student, and when my fellow young students in, say, the NAMD community or so, at the in the late 1990s, we were all kind of fighting and competing a bit. And it is, friendly competition is good, but I think in so many areas in science, friendly competition can become unproductive competition. And I think this started to become a bit unproductive, not necessarily, I think it was everyone's fault, it was the community's fault, that all programs were a bit too eager to get performance at the cost of doing shortcuts that people shouldn't have taken. So what's happened roughly the last 10 years or so, that all these codes have become much more strict about actually properly handling all this physics I showed you, so that we conserve energy, they're well-defined functions. And this is a particularly important reason why we can now predict things like free energy or so accurately. And at least to us, one important turning point here is that we realize that these other students, roughly the same age, when you haven't met them, you think that they're your competitors. And in one way, they are your friendly competitors, but your friendly competitors are really your closest friends. So that is one important memento mori here. Just because you're competing a bit in science doesn't mean that you should head out and drink beer with each other. It's a great way of friending them. I will skip the multiple time stepping too in the interest of time. So that somewhere where we are is that it's easy to see amazing, colorful pictures of gigantic systems, entire viruses, SARS-CoV-2, everything. But be careful there, because remember, the whole goal, as I just told you, is that molecular simulation works by reductionism. You want a very small system that you can sample efficiently, right? So that of these ones, I think that the system here in green is the nicest one because it's the smallest. This is just one molecule binding to one of the larger ones. A good scientist is the one who manages to reduce these large systems to a tiny part of her nerve cell so that we can get very long trajectories and good sampling. While the person who just draws that beautiful fancy images with 100 trillion atoms, that's the person who didn't even start to do their homework. So look for the small systems. In general, the smaller the system is, the better people have thoughts. The reason why that is so important is that as the size of your system grows, sampling sounds great, right? But one of the hardest things in the world to understand is the exponential function. And all these things grow exponentially. And trust me, even if you're professors, you have no idea how fast the exponential function grows. So even if we get about exponential things, that even if they just go by the second or third power of the size of the system, as the system grows from 1 to 10 to 100 to 1,000 nanometers, the number of atoms, it doesn't seem to go up that dramatically, but the times you need for diffusion will also go up. So that means that if your system becomes 10 times larger, you will have maybe a factor 1,000 more atoms, because 10 cubed, right? But that will also mean that you might need a factor 10 to the power of 6 longer simulations, or at least 10 to the power of 2. And the total simulation time you will then need to sample that will go up even faster. So a system of size 1,000 nanometers doesn't sound so horrible. There are certainly people simulating this today, but to actually sample that system, you would need simulations in the ballpark of 10 milliseconds. And what people instead do, they simulate this system, but only simulate it for 10 nanoseconds. And it might look beautiful, but it has absolutely nothing whatsoever to do with science, in my not so humble opinion. So what I could really encourage you, I think these communities, not just GROMACS, NAMD, by the way, and AMPER have great communities too, that simulation methods are powerful, but the danger is that we frequently become so obsessed with the computers and the technology that we stop thinking about the biology. And I think that is the single most dangerous mistake to do. I would say that in my group, I have two categories of physicists. The ones who are almost a bit tired of physics and really want to understand biology, they do great. While in some cases, the best physicists are the ones that find it difficult to be a bit sloppy and hand-waving with biology. And they might be great at the simulation technology, but they're frequently not as good scientists in a biological context. So these are, I can share these slides if you're interested, but in general, that think about the biology and think about the complexity. What is really the biological system you're trying to answer? And I would bet almost anything that you're not trying to answer the system of simulating a system with a 250,000 atoms for 100 nanoseconds. So go back, can you simplify this? Can you understand it? Is it absolutely necessary to simulate this? And that might sound like criticism, but of course, if there is this, in some cases, you can do back of the envelope calculations with pen and paper. And to this day, I think, as cool as I think simulations are, and I do think they're cool, it's so much cooler when I can literally take a pen and the pad and then scratch down something and give a student an answer. Well, based on an order of magnitude, it should be roughly this. We don't need a computer for it. it is also very dangerous that simulations will always produce an answer. And that might sound strange. Why is that dangerous? Well, the problem is that it's just a model. It doesn't mean that it's true. And I think I have some slides about that. Oh yes. So this is one example of this biological importance. So these happens to be membrane proteins that are ligand-gated ion channels, and it's not important. I'm not going to go through the detail here, but it's a very well-studied receptor called the GABA receptor, the gamma-aminobutyric acid receptor. And it consists of 5 subunits. It happens to be different subunits. And at the time, there were 2 groups in the world dashing to get the first structure out of this. And Ryan Hibbs, who I know very well, he was almost a bit disappointed because their first structure had one of these subunits collapsed almost into the pore that should be in the middle otherwise, right? He still got a paper out of this in Nature, was the first one to publish the structure of the receptor, so don't feel too sorry for him. But what we did about a year later together with him is that both in simulations and in nanodiscs in cryo-EM, we redetermined the structure with different types of membranes. So we actually determined this both with pure POPC membranes and membranes that contain a mixture of brain lipids or so. The caveat here is that you need this mixture of brain lipids for these to be stable. They will never be stable in an idealized membrane. And the danger here, I would argue that 95, if not 99% of all membrane protein simulations are done in these idealized membranes. Because people like me, physicists, we want a simple system, and we then forget that the protein itself might not even be stable in that simple system. And that's important, so that you need to understand the biology surrounding of the system that you're going to simulate. There are a bunch of tricks that you can do to improve sampling. Because remember, the sampling might not sound sexy, but everything we do is about sampling. You certainly want new computers, you want to use GPUs, you should try to use new software and everything. But here too, the best things, the fastest calculations are calculations you never have to do in the first place. Can you reduce the amount of water in your system? Can you, in some cases, Benoit Roux is a colleague in Chicago whom I adore, and he has this really cool things when the rest of us simulating an entire ion channel in an entire membrane, Benoit just takes 4 small helices and he puts them just with springs, because it's a model, it's not the truth. He's a physicist, someone who understands this model. And he has a system that is probably 1,000th the size of everyone else's, but he's able to draw really cool biological and physical conclusions from it. So simplify, simplify, simplify. Because that if you can get an important result with the first order model, you have much less to, he's not going to have to worry about the type of lipids he has or anything, because he doesn't have lipid in the first place. It's a simple model. There are a bunch of tricks that you can find in the GROMACS manual and others too, but in the interest of time, I'm going to skip these two. So that you want to take long time steps. You want to try to remove water or so, which we, in this case, occasionally GROMACS uses really strange boxes, but these are things that come from solid state physics that I bet that you all know. If you take a nice rectangular or even cubic box, right? The periodic boundary conditions are going to be obvious in the X, Y, and Z dimension. But in particular in crystallography, there are 20 different crystal classes, so that things like the shape here on the left, they will pack perfectly in space, but they're not going to pack straight along the X, Y, and Z axis. But the advantage here is that this is a better approximation of a sphere than a cubic box. And that means that we don't need as much water. It's roughly 20% less water. So that is 20% improvement completely for free. And there are ways to see this too, but I'm going to skip that too in the interest of time. You should be aware that GROMACS in particular can have some issues of showing this. Internally in GROMACS, we frequently use this triclinic boxes on the left. But remember that every dot you have here can also be drawn in a periodic box, one position to the left, right, or up, down, as long as we move along these box axes. So depending on what periodicity we put these atoms in, we can choose it to draw it roughly like this one. And here you probably see better that it corresponds almost to, it's a so-called hexagonal box. Or we can just say that let's base everything as if it was roughly rectangular, and then it will look like the one on the right. And here I've also made each lipid hole. as long as I fulfill these periodic boundary conditions, all these representations are valid. And that is something that users occasionally fight with when they're looking at output. But there's more information about this on the mailing list. So at some point here, you have a system and you know what you want to simulate, right? In practice, what we've spent a ton of time over in my career, or I shouldn't say that, what a ton of really skilled students and postdocs in my lab have spent a ton of time on. I only spent 4 years or 5 years on this. Is how do we make these things go faster? Because the problem is that molecular dynamics simulation was a great invention in the 1960s, but all these functional forms, everything that we did, that was designed for the way a computer looked in 1965. And computers have changed since then. It might come as a surprise, but they have. And the biggest change is that computers are now parallel. So when I was a PhD student, the largest computer at KTH had something like 200 nodes. And each of those nodes had 1 core. So there were 200 cores at the entire university. And if I could parallelize over 20 of them, I was ecstatic. A lot of work in GROMACS has gone into ways of being able to divide these things up better in space or so. I have a couple of slides of them later. I'll come back to that. The other part, though, is as we're doing things in parallel, we can go faster and faster and faster. But at some point, you start to realize, even if we simulate for a long time, maybe your protein starts to fall apart or so. It's not accurate enough. There were some big fights about this when I was a student, in particular for lipid membranes and membrane proteins up here. And at the time, we and a whole lot of other people, we just cut off all the interactions at 1.8 nanometers, straight cut off. And that was, of course, fine. Then there were some other groups that argued that you need this long-range electrostatic lattice summation from physics, which, of course, you didn't know. I was absolutely certain that you didn't know that, need that. And at some point in time, this debate became so heated and everything, so that I felt we're going to need to be able to do some sort of comparative analysis here to prove that you don't need this. And the way I proved that, I figured that at one point in time, I'm going to need to implement this type of lattice summation in GROMACS as a PhD student, just to prove that we didn't need it. Unfortunately, that didn't quite work out, because 1 month after starting this testing, there was some humble fighting here and everything. That's because our simulations too, suddenly they became exceptionally stable and much better. So 25 years ago, I think I started collaborating already when I was a student with Berkes and David van der Spel on GROMACS. And some of the first things I did was actually, I did them to show that they weren't needed. And in the 25 years since then, all of us, me included, have relied on that code. It's kind of fun. But this has continued. And so something that we've started to do over the last year is really move in this direction of improving things even further. So you might know a little bit about lattice summation, but just as an example of things that you would do here is that if you're having on the left here, this atom in the middle would have some sort of interactions with all the surrounding atoms. And what I would do before is to have a sharp cutoff. On the other hand, the actual electrostatic interaction, we know that goes all the way out to infinity, right? The trick that Eval did is that you can't sum this in direct space because then it doesn't converge. But what if you add to our direct space charges in black, if we add some sort of screening charges around them in red, that now means that the interactions in direct space will be closed very rapidly because it's screened, so that we can sum and make a count. But in reciprocal space, it turns out when I do a Fourier transform of these red dots, I get roughly the same type of shapes in reciprocal space. So the cool thing, instead of having one sum that is infinite, it doesn't converge in direct space. I get 2 sums. That's bad. But I get 2 sums that each converge. So I get one sum that converges in direct space and one sum that converges in reciprocal space. And to date, I understand the math here, but it's really, really cool that this works. I won't have time to take you through all the equations. I would say virtually everyone in the world in every single code uses this. There is a bunch of math here too, but it's not really that complicated. And it's probably 3 or 4 pages of code in GROMACS if you want to go through all this. Now, the reason I'm telling you that is that there is a second part here that both we and a whole lot of people ignored for a long time. And that has to do with Lennard-Jones electrostatics. So that's, sorry, electrostatics, I'm an idiot. Lennard-Jones interactions, that's all the things that are in electrostatics. So first, repulsion at very short distance and dispersion at long distances, that it's all these weak dipoles and atoms attract each other due to the electrons vibrating around the nucleus. Historically, we would do a cutoff here, and then long distance maybe have some sort of correction, long distance correction. But if you look at the original paper, it's actually quite possible to do this too with PME. The reason why we don't is that we use the system on the left. And at long distance, if you just close your eyes a bit, that's just going to be blue in general, right? That we can approximate that with some sort of average density. The problem is that what both me and my team have worked a lot on are things like membranes. And this, we have a complicated mix here, right? That there is no average structure here on long distance. It's going to depend on the layers. And that's even more true for things like membrane proteins, or so that for most systems are inhomogeneous and anisotropic. And then it's not as obvious that this long range corrections will work. So I'm not going to punish you with all the equations here, but some 5-6 years ago, I had a skilled student, Christian Wemberg, go through all this and pretty much copy everything from electrostatics. And there's an important memento mori here, that I think good scientists are frequently lazy scientists. And Christian definitely wasn't lazy, but if people have done other good things, learn from them rather than trying to reinvent the wheel. So what Christian was able to do is that for the first time, write lattice summation versions of the van der Waals interactions. And he was doing this in principle not that hard, and that has been known. The problem is that you end up with 6 of these lattice summation sums, and that's when everyone has given up. But Christian came up with a way to do this much faster, and we won't have time to go into exactly how he did it. But the point is that Christian's way of doing this is it's definitely faster than doing the type of old cutoffs at 16 or 18 angstroms that I would use. And what has now happened is that a whole lot of codes, in particular the charm force fields, they're being parameterized to use this Lennard-Jones PME interactions. My other reason for bringing up this is that I think this is a great example of a merit. So on the one hand, you have a scientific idea. You want to do something better. You want to model a system better. But remember that cost. Just modeling is not enough. The reason, because of this, if this bar had been 6 times as high, nobody would have done this. It would have been too slow. Yeah, well, we have the red one there. That's horrible. But by making this fast enough, that suddenly opens a door where people are not just willing, they're happy to use it. So I think a special thing in simulation models, all these computing aspects, is that on the one hand, with half your body, you need to think about the model, the physics, accuracy, the science. But with the other hand, you have to consider that you need the performance, you need the implementation, and this has to work efficiently on real computers. Otherwise, all that other stuff is pointless. And most successful projects, not just in my team, but in teams worldwide, have been able to combine those things. I'm not going to go through, these are some slides I stole, so I'm not going to go through exactly how we set up a simulation. But if you think about the large systems like this, what students and postdocs in my team have worked on with it is really, how do we take something like this, a biological problem, but then adapt it to this? So this turns out to be the logical units of a single processor in Skylake. A modern microprocessor is extremely complicated, and in this particular case, you have multiple vector units and everything, and I forget, I should know, but I think it can do 32 floating point operations per cycle or so. 32 floating point operations per cycle for one core. That's pretty impressive, but that's just one core. You can't buy a single core Skylake. Even my 5-year-old Apple Watch has 2 cores. This is a single modern CPU. Well, it's not even modern, it's Haswell, I think. It had 18 cores, and most recent AMD CPUs or so are going to have 32 or even 64 cores. So you have 64 cores where each core can do 32 fuse, multiply, add operations. So even a single CPU, remember, we only had 200 CPUs in the cluster when I was a PhD student. Each single CPU in your desktop, if it's high-end, can do in the ballpark of a few thousand floating point operations per second. So computers have become so parallel that I would not have been able to run GROMACS on one full CPU 20 years ago when I was a student. And that's just the CPU, right? Things get even worse. So when I was a postdoc, we started working together with some really crazy guys. A professor at Stanford called Pat Hanrahan, and I was with Mike Levitt. And Pat Hanrahan was a professor of computer graphics, and he had a really skilled PhD student called Ian. And Ian had an idea that we might be able to formulate my code, GROMACS, so that it could run on a GPU. And I think GROMACS was actually one of the first codes in the world that ran on a GPU, not this particular GPU actually, but this was this is a GeForce 4. The first GPUs GROMACS ran on were AMD processors. I even forgot the generation. And it didn't quite work. It was about the factor 10 slower than the CPU. So it was a miserable failure, hopelessly bad. And at this point, the student, of course, had to give up on this project, and he had to defend his thesis. And obviously, he didn't excel in biomolecular simulations. But he did pretty well, because this student was Ian Buck. And Ian Buck is now NVIDIA's vice president in charge of all accelerated computing. So everything that has to do with CUDA, GPUs, and everything, Ian is in charge of. And that's the other memento mori here. When you have good ideas, don't give up. Because both we, Ian, and quite a few other teams, we kept working on this. And it probably took us almost 10 more years before GPUs became fast enough so they started to overtake CPUs. And as you all know, today GPUs have not just overtaken CPUs, right? That they've left the CPUs in the dust. Everything is about GPUs nowadays. So dare to have long-term visions. There's a bunch of things we do here related to parallelizations and using multiple GPUs, but I won't have time for that either. The problem with that is that that's not going to work automatically, because historically we would have some sort of neighbor list. I've showed you that before, right? This red atom should keep track of what all the black ones are. The problem is that GPUs really hate this. Just the memory throughput would be too bad. So on GPUs and some other platforms, we've increasingly had to reformulate these ways, and exactly how we do it isn't important here, but instead of looking at one atom at a time, I try to look at groups of 4 atoms. They're not really bound to each other as I show them here, but this enables us to get by with data structures that is roughly 1/16 of the size. And we go even further in GPUs actually. So that's a third part to remember, that there is a very neat connection between science, algorithms, and scientific computing here that I to this date just love. You need to go back. Many of these algorithms that were fundamental truths in the 1960s, they're no longer true, because the modern computer doesn't look like a computer looked in the 1960s. Had you asked me 10 years ago, I would have said that I was so incredibly privileged to get a chance to be the generation that got to live through this and be able to reformulate the algorithms and move them to new computers. But you know what? This is true for you too, because right now everything is about GPUs. So I don't have an obvious slide for that in the middle, but this is happening again, only 15, 20 years later. Almost all these algorithms that we formulated so that I could at least port them to GPUs, they're already outdated, because GPUs are going to be so much faster that we are pretty close to giving up. These classical methods are not going to work on GPUs. Well, they work on current GPUs, but if GPUs get another factor 1,000 faster, which they will over the next decade, less than a decade, 3-4 years probably, we simply don't have that many floating point operations. And my gut feeling is that we will all be forced to move much more to machine learning, neural networks, and maybe replace these traditional potentials that I showed you, for instance, increasingly with machine learning based potentials. So both we and several other groups are working on that, but it's certainly it's work not finished yet. So I don't know what the result's going to be. And again, this is a transformation being powered by computing, which is, even as difficult as it is, I love being challenged by the computational industry all the time. So we have a handful, 3 or 4 people in the group who spend all their time looking at diagrams like this and thinking about the different functional units of modern hardware and where we can run things and make them fast enough. Now, having done that, when I go and present to the European Commission or so, I would boast about our scaling. And I do think that we scale pretty impressively. We can scale to hundreds of GPUs if my system is reasonably large. But the problem is, this is completely lost. I'm not sure if you saw the news yesterday that China has now run the first exascale runs on their computers, but even the next generation computers in Europe, they're gonna have hundreds of millions of cores and tens of thousands of GPUs. And me claiming that I have one very large system that can run on 400 GPUs, that's nothing to them. This is not, they will probably not even let me on the machine. And that's the other challenge I want to give you. This is an old slide and I've hardly updated it. I just added things to it. These were new machines when I first made the slide. In 2010, the largest machine had roughly 300,000 cores. That was Gene L. And if you just apply Moore's law here, that the transistor density would double every 18 months, you can extrapolate. And the point is that most of these numbers actually came through. These machines did appear. Pitts-Steins in 2017, well, they're not strictly cores, but these processor elements and GPUs, they are processing units. So at 2017, we were at 17 million cores. We definitely stayed on this path. 2018, 30 million. Summit, Summit were at 125. So this is actually not correct. We're moving faster than the green line here. 2020, 100 million cores. 2022, 300 million cores. I think this is roughly somewhere where we are already with the current exascale machines. And I'm not sure whether this is exciting or horrible if you're young, but the end result here is that by 2024, we're going to have in the ballpark of 1 billion functional elements or whatever you call them. So the key question you have to ask yourself if you're a student now, 2024 is going to be way before you have a chance to become professor. And if you want to have a career in these industries, the question is not how you can get your code to scale to 100 GPUs or 10 GPUs, but invert the problem. Ask yourself, how are you going to use 1 billion cores? And there is no way a single simulation is ever going to do that. And the second you accept that, you're kind of set free. Now, when this machine comes online, I bet somebody's going to take a gigantic system, like an entire cell, and then they put this in an MD simulation box, and then they simulate this for 10 nanoseconds. We have developed a time machine technology in Stockholm. So if you look very carefully now, I'm going to predict here exactly what the end state of this simulation is. So this is the beginning state, and then they simulate these cells for 10 nanoseconds, and then the end state will look like this. It's going to look exactly the same because there's nothing that happens in an entire cell in 10 nanoseconds. It will be a waste of CPU hours, but it will likely appear on the cover of a glossy magazine. But don't run that type of simulations. What I would like you to do instead of think of ensembles, because this is where I see the field going. There is an amazing diversity of smart new techniques. And there are so many techniques that you can likely invent your own techniques too. And I won't have time to go through all of them, but I'm going to talk a little bit about Markov state modeling, which is one of the techniques that we have used. So the idea is that if I just run lots of simulations, these simulations are going to visit lots of points in this so-called phase space. And after a while, if I stop, I might realize, you know what, there are some regions in phase space here where lots of these simulations tend to aggregate. So I get lots of confirmations. So let's group those into some sort of clusters. That's easy to do. And then we somehow try to discretize this space and realize, well, we spend a lot of time in the blue and the yellow one, but how frequent is that if we are in one state here, sorry, should have used the same colors. If I am in yellow, what is the probability that I either stay in yellow, P1, or move from yellow to red, or from red to yellow, or stay in red? And this is the physical concept of a Markov chain. So that the idea with a Markov chain is that all that matters is where you are now. There is no history, there is no memory here. And this works great once you start clustering things on a high level. And as we simulate more, we can expand this map. So the whole idea with this map is that literally by taking our glasses off and just trying to look at the large scale motions, you don't worry about the rattling on the very fast time scales of the protein, but really try to what happens, what is the likelihood, for instance, this ion channel opening or closing, but don't try to look at every single side chain vibrating. The reason why this is so powerful is that as I'm starting to have a few hundred states like this, I can easily run tens of thousands of simulations. And this is something that we've used very successfully, first in folding at home, but today we're doing this on supercomputers all the time. So this is an old example that I'm going to skip in interest of time, but Catherine, one of my students who is literally working on ion channels, to date, none of us had been able to simulate the entire gating, opening or closing of these channels. But Since we had both open and closed structures from the experiments, what Catherine did is that she took these channels and interpolated between the open state and the closed state. So these are really very rough initial guesses. And then she used that to start roughly, I think it was something about 100 or 1,000 simulations, each covering roughly 1 microsecond. But they didn't, each simulation just had to run on one node or one GPU. They didn't have to run in parallel. And based on that, we can then start to map out the entire free energy landscape. So under what conditions would the channel like to be open? Under what conditions would the channel like to be closed? And the cool thing is that she can then reproduce how changing the pH will actually open or close the channel. But now it's no longer based on hand waving or say, oh, maybe the channel was opening or maybe it was opening a little bit. Suddenly we have this quantitative. We can show that with 95% certainty, if I change the pH, these two states are going to trade places. And then we come back to these quantitative predictions that I try to stress to you, that I find this much more quantitative than a single simulation movie. That's actually one of the reasons why you rarely see me showing that many movies in the talks. Movies are beautiful, but hard physical data beat them. I would also strongly advise you to keep things simple. And I won't have time to go through these results, but if you just look at what I published the last few years, that many of our high impact papers actually just have maybe 5 or 10 simulations of a microsecond, maybe 2 microseconds each. But I think we've been better, in particular my colleagues and students here have been better of injecting very large amounts of solid data into them. Today we virtually always compare the experimental data and try to either do the experiments ourselves or collaborate with a group. And we could run larger simulations, of course, but there is no prize just for running long simulations. The prize is writing good papers and getting insight of the biology. So you don't always need the largest supercomputer to do that. In the interest of time, I might going to stop there, but the whole point, there are a bunch of things here. In some cases, it's simply that I didn't have any better idea, then we had to run a long simulation. But to date, I still get this childish feeling that the simpler and shorter the simulations are, the more beautiful and cool they are. So if you ask simple questions, in general, you will have a greater chance of finding simple models. And this simplicity, long-term simplicity tends to beat complexity when it comes to model and publications. Scientists, we are fairly simple-minded and we like simple answers. There are a bunch of things here that I won't have time to go through, but I really want to finish off here by mentioning that you've probably seen this magnet picture, right? This is not the pipe. And the point of the picture is that it's not the pipe, this is the picture, there's a painting of a pipe. But that is also not true, because what you're seeing a pixelated JPEG shown over Zoom, which is a scan of Magnet's painting, which is a painting of a pipe. And all those things are, of course, orders of models. And it is important to be aware of this too, because this happens in simulations too. And this is something we didn't publish, but that happened almost 10 years ago. So I started my ion channels, and this is a channel that under particular settings we could get the pore either to be open or closed. And then I wanted to see, can I mutate these residues now to get it to be even more open so that it's open even at high pH? And then we mutated these to serines, and you can see how open this pore is. This is amazing, right? And then we went into the lab, and I'm not sure if I have that data. Yes, the mutations resulted in a channel that was not more open, it was more closed. And at that point, I was willing to start eating my humble pie and stop doing simulations. But in hindsight, what we realized is that we had now introduced 10 negative partial charges, at least here. So what's happening now is that the positive ions that we were normally conducting, they are likely binding inside the channel instead, which to a structural biologist is very obvious, right? But the difference here is that in the experiment, you measure ion conductance. In the simulation, we basically measure the radius of the channel. And those are different things. And in hindsight, it's obvious, but it wasn't obvious to me at the time. So again, don't fall too much in love with your simulation, but really remember to think about what this would mean in the experiment and what the experimental results are, because they might point in the other direction than you think. I think we're pretty much out of time here, but I'm going to spend just 2 more minutes on the last 2 slides here. That science has gotten both harder and more competitive, which I think is good in some ways, but it's also challenging if you're a young scientist. I think I was probably part of the last generation, at least in large parts of Europe, where I think I did a reasonably good PhD. And then I went abroad and did a reasonably good postdoc with Mike Levitt. If it wasn't good, it wasn't Mike's fault. It was my fault and those shortcomings. And then I was lucky to get some funding to return to Europe. And when I was back in Europe, I get an offer I applied to it, but I got the position fairly early on. And that's pretty much the path that set me on. And since then, I've had funding from the Swedish Research Council and had various forms of tenure or professorships and everything. And now I have the world's most amazing group with so many talented people. But Jesus, am I happy that I'm not applying today, because the competition for positions today is insane. In general, I think that's good, because it means that there's so much more mobility all over the world. Universities actually seek the best possible talent, not necessarily the old Swedish postdoc that they knew is currently working at Stanford and they would like to have him back. For Mike's sake, it's good that they did that. But the point is that at least long term, there is roughly the same number of positions in the world. There is, of course, many more people doing these things. And I'm not going to say that it's easy to get positions, but frequently, and today I'm Vice Dean of Chemistry, and I frequently sit on the other side of the table. And if there's one consolation, it's that if you think that it's hard finding jobs, it's just as hard finding candidates, whether it's candidates for PhD positions or postdocs or assistant professors. And it's not because candidates are bad, right? But we're looking for a particular fit. Maybe I'm looking for somebody who's an expert in cryo-EM, and it doesn't help that there are lots of really skilled people if they're not good in cryo-EM. So don't get worried if you feel that you have to apply to 10 or 20 positions. In my days, we didn't have to do that, but that's because there wasn't as much competition. Today, people look longer, they want more diversity and everything, but the price for that is that you might have to apply to more positions before you find one that is a good match. But that in turn makes all these other things, participation in communities, more important. Go to workshops, even if you might not feel that you're an extrovert, participate in forums and everything, because this is basically how people get to know you. And having some sort of track record that you're doing things appreciated by others is going to be great for your career. I once hired Mark Abraham as a postdoc when he was in Australia, and I've never seen him in person. But I'd seen what he had done on our mailing list, and I figured that I would pay anything to have him in Sweden. And that turned out to be one of the best recruitments we ever did. So some of these recommendations are more specific to GROMACS and simulation software, but I would argue that they are also fairly general. Engage and be generous with your time. Try to help. Don't worry too much about contacting people, but contact them in a way and suggest, is there anything you could help them with or so. But in general, the one recommendation, mail them in open forums. Don't use their personal emails, because they might have already answered 900 emails in that same topic. And I won't say that every single one of them is certainly a nice person, but if they're not a nice person, you probably don't want to work for them anyway. So there's nothing to lose in the end. So to sum things up here, this was a bit of mix and everything. There are limitations to MD. It is not magic, but once you realize what those limitations are, and in particular combine this with experiments, I think this is a really cool and nice method that will keep evolving. But if there is one thing to recommend, that you need to think about what your analysis and biological question you're trying to answer is before you simulate. Don't just put a protein in a computer, push the button, run the simulation, and then think, what kind of analysis am I going to do? You need to know the analysis before you start the simulation. You should always keep this in mind, that what you have is simulation of a model of a protein. This is not the protein. And just as my ion channel didn't open easier to channel, because you see something in your simulation on the screen, it doesn't necessarily mean that the protein will behave that way in reality. Now, that is boring, that is irritating as hell, but the only thing that's worse than that is if you don't check. Because if you don't check, you're going to publish things that are incorrect, and then other people will point out that you're incorrect, and it's much better you find out yourself. So somewhere there, I had a beautiful career, and I think that many of you will have too. This is an amazingly expansive field, and the computers have only seen the beginning of their power. And 10 years from now on, half of you will have overtaken me when it comes to machine learning and everything. But I think that that's the cool nature of this field. The half-time of some of the knowledge in the field has a half-life of 5 years. So all those things I learned in the 1990s, they're completely useless because computers don't look that way anymore. So it's fun trying to keep up with you, though not necessarily easy. With that, I'm going to thank you for your attention. And there are a bunch of people in Stockholm over the years that have helped both with GROMACS of the code. I won't have time to go through and mention every one of them, but none of them is forgotten. And I'd be happy to take any questions you might have.
Perfect. Erik, thank you very much for this great talk and all the advice and the good perspective. We ask the participants to submit questions if they wanted when they signed for the seminar, and David has done a very good job in trying to go through all the questions and try to group them and all that. So we have picked a couple of questions from there. We will start from there, and then we will open the floor for the rest. So and of course, among the questions there were questions about machine learning and how GROMACS will either be affected to or move on the direction of machine learning, and you have hinted a little bit to that on your talk. We also see it in our day-to-day work. I mean, we use a lot of energy and time to do free energy perturbation calculations on small molecules binding to proteins, and we also can have now machine learning models that can learn those and can do the predictions in a fraction of time. So if you can kind of elaborate on this very broad topic, of the impact, both how machine learning,
yes.
Yeah.
Machine learning in general is interesting, but the problem with it is that there's a lot of hype. And I think this is a fundamental shortcoming in science, that people only publish positive results. And I would say, that's another reason why people should go to conferences, because I don't think people are hiding things. It's just the natural dynamics of publication, right? I don't publish negative results either. But of course, if the second you start to talk to them, they will so confess, oh, but this is not ready for production. You can't actually use this to simulate a protein. It's just a small proof of concept. So what happens with machine learning is that you have a very well-defined, and this is not specific to MD, if you have a very well-defined set of training data, and that could be free energies or anything, machine learning is in principle just very fancy interpolation. At this way, it's not quite interpolation, right? But it is interpolation in the sense that the computer is seeing the pattern. There's no special intelligence here or anything. And of course, if you have enough data points and if there are clear patterns here, the computer will be able to draw the lines between them. The problem is that, of course, if you're extrapolating, if you're not going to need to make a prediction in an area where you have no points, all bets are off. And that has happened in fairly tragic ways. That's why there have been these occasional accidents with Teslas, right? One of the first accidents was that a Tesla drove straight into a semi-truck because the truck was white. So it interpreted it as heaven. And so who on earth would ever design a software to do that? But the problem with machine learning, you can't say that, oh, but if it's heaven, if it's special. You're giving over control to this network, and the network makes all the decisions. So it becomes one of the hardest things in machine learning is to know when are you falling outside of this training regime, because there's not going to be a red sign that tells you, oh, but now you can't trust my results. And what happens if there are cases where people try to simulate proteins. The problem is that proteins blow up after a while, after half a nanosecond or so, or implode so that all the atoms it's like a nuclear bomb. And of course, once it has happened, people, of course, realize that something went wrong here. But when did things go wrong? That is very hard to say. The other problem is that today machine learning is still probably a factor 100, if not a factor 1,000 slower. And remember some of those first results I showed that if all we wanted was accuracy, we would do quantum chemistry. And the hard thing with MD and free energy is that you need the balance. All other things equal, I would instantly take a more accurate model, but all other things are not equal. I also need the sampling so that I cover a large enough part of phase space. So of course, if you're making the energies a factor 1,000 times better at the cost of making the sampling a factor 1,000 worse, we're probably back roughly where we started. But what people are going to publish is that their energy is 1,000 times better, more accurate. But it's not solving the problem. And this is this hard part, right? It's not that easy in practice. I think I am fairly hopeful that over the next decade at least, first GPUs are going to get so much faster that at some point it will not be a factor 1,000 more expensive to use so-called inference rather than calculating Newton's equation of motion. We're going to need to find, now I might tell you the details of my next big grant, but don't post all this on Twitter. We're going to need to find ways of combining these type of old style Lipson style equations, force fields, with machine learning, either by using machine learning as a correction or training machine learning as a way so that you kind of have two networks. This is what you would have on a modern Airbus plane. So you have 3 computers, and as long as at least 2 of those computers agree, the computers run the plane. If the computers don't agree, they disconnect and tell the pilot that you have to fly the plane. And you probably could do something similar here, that if you have multiple independently trained networks, as long as they agree, we'll let the network do it. But if the networks don't agree, we have likely fallen outside of their training regime, and then we need to go back to the Lipson style force fields or so. The other part is that, remember what I said, what was our original problem? And the original problem likely wasn't to run a simulation for 100 nanoseconds. The original problem might have been to understand the motions and the dynamics in the sine channel. So another thing that we're toying around and working with, maybe we can get directly based on cryo-EM data, which frequently represents a few different conformations. Maybe we can get these neural networks to directly generate the entire landscape of these structures. There is no extra price for doing this one tiny step at a time. But then we haven't done that yet. I have no idea whether it's going to work. So machine learning is even more of a Klondike, where have an idea, test it. You're likely going to be the first one to test your particular idea, and it can't go worse than miserably failing. But yes, I'm convinced we're all going to do much more machine learning over the next 10 years.
Yes.
But just don't believe all the hype in the publications.
Thank you. Okay, we have one more question from the previously submitted.
Yes, so thank you, Dr. Lindahl. That was very engaging and interesting talk. So there are a few questions that we saw repeatedly on the form where people enroll themselves. And one was asking if you can comment a little bit on how does GROMACS compares to alternatives such as NAMD, LAMPS, and AMBER, like what are the pros and cons, and when you might want to use one or another, or if GROMACS is just superior to all of them.
No, so one thing that I'm very clear in my team, nobody in my team has used GROMACS. I tell all my students to decide themselves what code they use. But there is a price for that, of course. Once they have a problem, they can't come to me and say that the person you made a choice about the code you wanted to use. Start reading the source code and use the forums and be a responsible scientist. It's not my fault what code you chose to use. Having said that, there are some general things. These are not things that are better or worse. It's just that these codes have been designed to target different areas. I can start with LAMPS. LAMPS is a really amazing code in some ways. It's super modular. It probably supports 3,000 or 5,000 different types of potentials. If you're working in material science and need a particular cobalt machine learning trained, I don't know, whatever. Now, any esoteric strange potential that somebody derived in 1964 and there was one paper on it, I bet it's going to be implemented in LAMPS. You have every single potential in the world there. Now, the price for that is that, of course, if you need those potentials, it's kind of stupid to try to use GROMACS or NAMD or CHARM because they're not implemented in those codes. So we kind of lose and walk over, right? But if you use a plain protein simulation with Lennard-Jones and Coulomb, the price you're paying in LAMPS for the generality is that it's going to be very slow for those general potentials. And I never do benchmarks because they're always out of date, but we're talking about at least an order of magnitude slower than any of the other codes. And that's not because they're stupid, right? It's just that you can't do hand-tuned GPU implementations of 5,000 different potentials. It doesn't work. So they had to go for generality where we could cheat in a way and just optimize it for biomolecules. GROMACS and NAMD is fun because that when I was a student, it was that GROMACS had really good performance, much faster performance than NAMD, but our scaling was completely miserable. We couldn't scale more than 10 nodes. That has kind of changed over the years because that first NAMD started to become better at GPUs. I think GROMACS is still faster in absolute terms, but in the latest few versions, we scaled better. It's not a whole lot better, but a little bit better. And I like this way. I think it was Scott Legrand, who's now no longer working on Amber. We had this beautiful thing that we keep each other honest. And I like that I don't do benchmark, because the benchmarks are kind of like cars or computer models, right? They change every time, every year. But we collaborate a lot nowadays, and we frequently compare codes against each other. So that I sit on their scientific advisory board for the Center UI UC. So that for all these codes, there will be any code you pick, there will be algorithms that are only implemented in one of them, and there will be, God forbid, but there are bugs. There are bugs in all of these codes. So in particular, if you have something that doesn't work, trying and being able to use another code is probably a pretty good idea.
Thank you, Erik. There are some questions coming from the chat, so I'll take the first one. It's from Vijay, actually joining us from Tanzania, which is very interesting. And he is asking, how can you, train students in machine learning having limited resources? And I understand here is just computational resources. So if that is a limitation, or if it can be done.
I'm sure it can. So first, I'm not sure what specific local resources you have. That when I was a PhD student, I think one of the reasons why GROMACS, why we never bothered to scale GROMACS, and we probably only had 20 computers in that, and we could never get more. That's in it. While NAMD at the time, we had Klaus Schulte and access to the largest computers in the world. They had 5,000 cores. So they had orders of magnitude more resources than we had. I think we did fairly well. So they did well too, right? But it's certainly nice to have lots of resources, and it's nice to be spoiled as a student, but don't for a second think that you're necessarily doing better science just because you have more computers. Science has to do with thinking, and that you're doing with paper and pen. And I would say the same is largely true for machine learning. Sure, there are some amazing papers on AlphaFold 2 or something, but if you're learning this, there's a whole lot of theoretical work that you could do in a very low-end GPU. And I know that both companies like NVIDIA, Amazon, first, they're reasonably cheap resources available online. And if you ask them and have a good cost that it's related to teaching at a university that is strapped for resources, they might not donate tons of hardware to you, but you don't want to take care of that hardware anyway, because then you're going to need to pay a sysadmin. But they might offer you some free time on their cloud or so. So it's get in touch with people, in particular companies, and see if you can get some sponsorship there.
Excellent, thanks. And to the audience, I am not going to bore Erik with specific questions you can post on the GROMACS mailing list. So that I dictatorially will not put here. So
there is no activity now, but we're thinking of it. It might happen in a year or 2 or 3.
Okay. So you're reading them. I have one from Jagannathan, which is of course a question about the accuracy of the calculations, right? So how accurate are the computational results, and how well do they correlate with experiment? Which I find it interesting now that you have your group, which is spread also, is doing experimental work as well.
That's a very difficult question, because in that question there seems to be an underlying assumption that the experiment is right. And that is not necessarily the case, or rather, an experimental result is always correct under the conditions you ran the experiment, right? But then you have to be very careful with that experimental result. And that experimental result is not the coordinates in the PDB file. That experimental result is the 3D electron density, for instance, from our cryo electron microscopy experiment. So first, we took a protein, we purified it, we pulled it out of its native membrane. We now have artificial lipids. And then I'm freezing this at 100 Kelvin. I'm starting to be pretty far away from a normal synaptic environment, right? So I've changed things here. And we know that these things influence it. And then, of course, I do approximations when I cluster things. So this is not to say that experiments are wrong. But there are errors or shortcomings in simulations, but there are also errors, shortcomings in experiments. And how severe these are, you can't say. That's why we have scientists who publish papers on them. And that's good, because otherwise we would be out of business. So I think the only recommendation I can do, look at multiple sources and try to understand why you're seeing the results you're seeing. I would never, ever blindly trust a simulation. But on the other hand, I would never ever blindly trust an X-ray structure either nowadays.
Super, thank you. I see Angelica is educatedly raising her hand, so please, Angelica, go on.
Thank you. So I have a question about like, first I want to thank for GROMACS. It's like this open source tool that is like super powerful for all of us that are doing MD. So I want to know what are your comments about like these other tools that are also open source that are starting to appear like in the USA, like OpenMM, and how it affects GROMACS. And also, how is the maintenance of an open source tool so widely used, and how is that maintained over the time?
I think that the first part of the question comes back a little bit to all these codes, right? The codes are developed for different needs. So OpenMM was a code that I was even partly involved in designing it from the start. So that was partly based on our needs of folding at home and being able to design things that could rapidly create new structures. OpenMM is neat in the sense that if you want to be able to drive things from Python, the limitation with OpenMM is that it doesn't parallelize. It can't use more than one GPU. While again, partly because we've had lots of resources and partly because all the GROMACS accounts for something like 5 or 6% of all supercomputer cycles in the world. So both Intel and NVIDIA and AMD have staff working on it. So whether we wanted it or not, that's why we have all these vendors investing resources and porting this all GPUs. Even the new Intel GPUs that are not even released, hardly released yet, they already have GROMACS acceleration. So that I think a power for GROMACS, we have the performance and we have this broad support everywhere. Sometimes that makes me mutter a bit because it also means that you end up with lots and lots and lots of functionality in the code, and some old functionality can of course be buggy, but I think diversity is good. I would be much more worried if we only had one simulation code in the world, because then bugs would go undetected. I think there are lots of bugs that are exposed in these codes simply because you're comparing with another code or two and you don't get the same result.
Excellent, thanks. I see Hafiz also is raising his hand, so maybe you can ask your question.
Hi, Professor. How are you? And it's nice to have you on that very important topic on GROMACS. I'm facing a problem while using the GROMACS. I have 2 GPUs in my GROMACS system. One is RTX 380 and other one is RTX 370. I want to use both of the GPUs for a single simulation, or both of the GPUs for 2 different simulations. While I'm doing simulation on both of the GPUs, I have used different commands and I have optimized it, but the maximum result which it shows that both of the GPUs, they work up to the 60 or 65%. They used their capacity. So I want to use them.
Those things can happen. I can't say anything about this specific simulation system. That's probably better suited for the mailing list. But what happens with GPUs is partly related to what I said. In some cases, the CPUs are just too fast for the system, so you can't saturate them. The other thing that sometimes happens is that the computer is too slow, because if you're running on multiple GPUs, modern high-end GPUs can occasionally talk directly to each other, but consumer GPUs or older ones, they have to go through the computer. And the problem then can be that you spend so much time for the GPUs talking to each other through the computer that they don't really spend any time doing the calculations. So it can unfortunately happen with slower computers or very small systems that it simply doesn't pay off to use a second GPU. But there are some, in particular for newer GPUs, some of the most recent GROMACS papers have fairly detailed benchmarks for this and how good the scaling is with multiple GPUs and how to do it. So there should be a reasonable amount of documentation online, but post in the forums otherwise, and people will hopefully get back to you with the details.
Excellent. Thanks for your question. Hafiz, we'll leave the word to others now. You and I think Erik has addressed you to the right place. So
Silla
Olga,
knows
can you
those things
please?
much better than I anyway.
Olga, I see Olga has her hand risen, so please.
Thank you for the very nice and inspiring talk. I would like to come back to the question of the computational experimental type of project. I have the impression that the experiments can go very far, or very fast, rather, compared to what we can do in a computational project. Then I would like to ask if you have seen, like, in your experience or in your career, is there like some tips that you can give us when we engage with experimental collaborator to make a good connection so that it will be the most successfully possible?
So first, I would say that we have some experimental papers that take 3 or 4 years to get out. So that in particular in structural biology, you can wait for a very long time. And if you're unlucky, somebody else determines the same structure and then you're scooped. So I would say in general, it's easier to publish simulations than experiments. With simulations, I would say be careful what you run. It goes back to don't just run long simulations. So there's both a curse and a blessing in all type of computation, because this is about statistics, right? So that in most cases, when you're collecting statistics, if you're doubling the amount of data you have, the standard error will only go down by the square root of 2. And that means that if you have some sort of data and then you would need a 10 times shorter standard error, so 10 times more accurate result, you're going to need a factor 100 longer simulation. That's the bad side of seeing it. But what I always try to encourage you to think of the opposite is that, but what if you only run your simulation for 1/10 of the time? You will only lose the square root of 10, which is roughly 3 in terms of your accuracy. So many of those things, sure, you couldn't submit that to a paper. It's too noisy. But in very many cases, you can see the first signs of early data very quickly. And that's exactly how we do this in cryo-EM too. So when we purified the protein, when we put it under the microscope, 2 days later, we typically have the first very rough 3D densities. And I have no idea what it's going to look like. But at that point, I know this is going to lead somewhere. It's worth investing 12 months of a student's career in this structure and try to get a paper and a high resolution structure of it. And I think it is useful to try to think the same way about not just simulation, but any type of theoretical work. Can you come up with a limited amount of sampling or so just to get a gut feeling, or try to test 2 systems, like do both of them move in that direction or do both of them move in that direction, to get some early quick data to confirm, is it worth spending more time on this? But what I tried very hard to avoid, but it does happen in my team too, is when people first spend 6 to 9 months running things and then start to simulate data. Because the students who do that will frequently realize that there was one problem, and then they have to simulate those 6 months again 3 months later. So try to design simulations so that you can start analyzing data very quickly. Never wait for months before you start analyzing. But exactly what to do will depend a bit on the project.
Thanks, Erik. Juan has another question from the pre-compiled ones.
Yeah, one that was very common was regarding, like, when you're starting a project, you have your system and you have some computational resource that you have access to. So can you give us some pointers on how to choose the best set of parameters so that you can maybe use your resources better so that you can have like the best performance? And if GROMACS has any plans on doing this more automatically, say to make an automatic choosing depending on the performance that you get with your machine.
GROMACS does a huge amount of automatic tuning already. The sad part is that you don't notice it because you don't see it. So for instance, depending on how fast your CPU is versus your GPU, we either push more things on the GPU or more things on the CPU. We adjust the neighbor list lengths on the fly. We decide, are we going to run multiple MPI jobs or multiple threads? We determine that depending on the vendor of your processor and everything. The instruction sets we're going to use, we optimize that on the fly. The problem, and depending on the size of your system, we decide how many GPUs we're going to use and everything. The problem is that there are so many things you can run in a simulation. Are you doing free energy? Are you doing computational? Like, there are probably 500 different types of simulations, right? So the problem is that most of these things we've done are heuristic and a bit of semi-manual wise choices. So I think long term, we will have to move to even more automatic choices, so that in the sense we load balance this on the fly. So not based on the tuning that we've tested this and it should be 0.7, but let the computer figure this out. But you can imagine if you have 2 CPUs and then 4 GPUs, the first assumption is, if GROMACS starts, do you want GROMACS to use all these resources or half of them? That depends. Are you going to start a second simulation? And there is no way for GROMACS to know that when you start your first simulation that, well, we haven't done the time machine technology yet. So in some cases, are you going to use 4 different simulations on your 4 GPUs or 1? And there were some things like that simply will have to be specified by the user. So Szilard, there's some information on this in the install and user guides. And I know Szilard Powell has given a bunch of talks and everything that you can likely find on YouTube about how to tune GROMACS in practice, different ways. So that it's probably not in the manual, but Szilard has given some really good talks about this. So in general, long term, it will be more automatic, but long term, the hardware will get even more complicated. So we will probably at best maintain status quo there.
Yeah, I guess that in general, it's also like you mentioned in your talk, it's better to just run multiple replicas of your system and therefore have a better, like in general, a better performance and a better sampling. So that's something that I.
So what I would generally recommend is also, again, walk before you run. Start by only running a simulation on 1 GPU. And then there are a couple of tools in the DSMI, for instance. You can check what is the load on my GPU. Am I using 100% of that GPU? Check what performance you're getting. And that might be your baseline. You probably want to try without the GPU first to make sure you shouldn't run on the GPU unless it's faster to run on the GPU than this, because you could have a really old GPU, but a brand new CPU, and then it could be faster on the CPU. If you're going to run on 2 GPUs, well, check the performance. Is this faster than running on 1 GPU? Which is not obvious. If you have a very small system, we might not be able to scale, or it might be faster, but it might only be 10% faster. And you probably don't want to waste both your GPUs for just 10%, right? Then you would probably prefer to start a second simulation on the second GPU. But the only person who can determine this is you. We can't say automatically whether you intended to use both GPUs or not. So that check that you will see what the performance is within 1 minute. And then just make a small table, and based on that, decide for this particular system, it's likely worth doing this. But it's very rare that we run on 4 or 8 GPUs. It happens, but in most cases, we have more than 1 simulation.
But I think considering the time here in Sweden, we probably will run with 1 or 2 more questions and then let Erik go, to his family.
I can also say, I can so encourage you to post questions in the GROMACS forum. We have 2 people on parental leave right now, so we're not quite as good as well, but we try to have some activity there. And the only reason why I tell people not to mail me is that I get 600 emails a day, and right now I'm busy with a big application. So it's not that I actively ignore them, it's just that I might not be able to prioritize them, and 2 days later I've completely forgotten about them because there are 1,200 emails down in my inbox. So you will usually get A, better support on the mailing list, and B, that means that other people will also be able to read your answers, so we kind of build up this knowledge bank. That's why we prefer to have questions there.
Yes, so I think we can probably take the last one, which also we compiled from the pre-established questions, and it's about now in the good old times you ran 1 simulation, you were happy with it, and that was it, right? Nowadays there's no excuse not to run more than 1, right? So it's more about the replicas, how many, how when should you stop running replicas of the same type of simulation, and more general, of course, you alluded a little bit into this, how to use all these small simulations, which is probably, the Markov state modeling of the different landscape that you are starting to map with the different simulations. So if you can just to conclude, walk us a little bit through those.
That depends on your algorithm. So imagine if I have an ion channel and an open state here and a closed state here, and then I can just interpolate between them. So I have 100 points. The trick is now, if these 2 points are next to each other, I need the sampling of these 2 points to overlap each other sufficiently, because otherwise it's not a continuous, I need to have a continuous sampling all the way to open to closed. So the length of these simulations need to be long enough that they actually sample the local vicinity around each of these points. If this is a gigantic system, I might need to add more points because 1 or 10 microseconds might not be enough. Or in some cases, if it's a very small system, 100 nanoseconds might be enough. So the whole point, we need to get statistical overlap between the sampling. There was one more question that I can answer about Charm, whether we have any GUI. We have one. It's called Charm GUI. So Charm GUI is not really specific to Charm. It works for all these codes, not just GROMACS, NAMD, and you can even run GROMACS from DMD. And my reason here is that I'm no longer a young student. I have fairly generous funding and I'm reasonably powerful in this world, that I don't want to get into the habit of stepping in. And of course we could develop a GUI for GROMACS, but what would I effectively do? First, I would duplicate the work of somebody who's already done really good stuff, such as One Pilin on Charm GUI. Second, I would take his livelihood, because all GROMACS users had previously cited his paper. So this is a person who's been really nice to me and written a really nice tool for my code. I don't think it's particularly nice in return to steal his entire scientific basis, right? And just copying him. And the same goes for, we don't want a molecular viewer, because I know John Stone is the smartest person in the world when it comes to molecular viewers, and he supports GROMACS. So of course I want to work with him, not against him. So what we try to do for most, we're kind of hesitant to start building our own versions of good tools that already exist. We think that I prefer to see this as rings of knowledge that spread on water and engage the entire community rather than me taking over the community. So that's mainly the reason why we don't do it. MD analysis is also a very nice analysis package that you can use with GROMACS. And I don't want to beat them either. Which is good because they're much smarter than I am when it comes to the analysis.
Perfect, excellent. So I think, for all the others that got your questions not answered and still have your hand risen,
post them in the forums.
Yes, exactly. Please do that. Please do that. And Erik, thanks very, very much again. And hope to see you soon, either here in Gothenburg or in Stockholm at some point.
My pleasure. Good talking to all of you.
Yeah, and good evening, afternoon, wherever you are. So bye, and thanks very much. Bye-bye.